All right, everybody. Welcome to Chapter 5 here. This is going to be the first lecture video for Chapter number 5 here. The very beginning of this chapter is talking about chemical bonding as a whole. The rest of this Chapter 5, though, is going to be specific to ionic bonding. And as we kind of start to talk about this idea of what chemical bonding is, when you've got two different elements or whatnot kind of bonding together to form a compound, right? What does that look like? What are the differences between the different types of chemical bonding that you're going to experience here in this chapter as well as our next chapter and all that good stuff. So without further ado, let's talk about again just chemical bonding as a whole, right? What are the different kinds and what do they entail and how do we kind of differentiate between the different kinds of bonding? Okay, so Chapter 5, which we're getting into right now. And our next chapter, which is ultimately going to be Chapter 10, these two chapters describe the model used to explain how matter interacts with each other. So recall that a model, if you remember way back, a model is any kind of mechanism a scientist uses to explain an observed phenomena, right? So again, all the different types of models we've talked about in the past, more often than not, the models you guys are utilizing and seeing throughout this class are our models of our lab write-ups, right? So all the different tables we put on there, some of the graphing we do, especially with our most recent lab, we've done some graphing. Some of the calculations we do, right? These are all different types of models we use to describe observed phenomena. So for example, an observed phenomena might be mixing a piece of sodium metal in water could result in a fiery blast and fizzing noise and produced sodium hydroxide and hydrogen gas as products. Okay, so the model to explain that would then be electrons are arranged to form new substances. The way the electrons are arranged are called bonding, right? And that's essentially what happens here, right? That's why I've mentioned so much over the last couple of chapters previously how important electrons truly are, right? We spent an entire chapter basically in Chapter 9, our most recent one, talking about electrons, right? Electron configuration, what happens when electrons move up and down different principal energy levels and whatnot. Electrons are so incredibly important, and that importance doesn't stop here, especially when talking about bonding. Okay, now plain and simple, guys, a chemical bond is just a force that holds two atoms together, resulting from the sharing or transfer of electrons, right? And that difference there plays a very, very important difference, whether electrons are being shared or they're being transferred, right? So it's very important to make the distinction between what's being shared and what's being transferred. Now, in that same vein, right, trying to figure out which one is which here, an ionic bond is between a metal and a non-metal, or a metal and what's known as a polyatomic ion. And we've not really yet talked too much about polyatomic ions just yet. We're going to save that for a little bit later in this particular video here. But we are able to for sure differentiate between what is considered a metal and what is considered a non-metal, right? All we have to do is look at our periodic table, identify where our periodic staircase is, like on the far right-hand side there, and make sure that if you've got two different elements that are seemingly bonding together, right, their atoms are bonding together, as long as one of them is a metal on the left side of that staircase and one of them is a non-metal on the right-hand side of that staircase, that is going to constitute as ionic bonding, right? And then also bringing into the fold this idea of what a polyatomic ion is. Now, whenever there is ionic bonding, this indicates a transfer of electrons. So if we quickly go back to our previous definition of chemical bonding, right, it results from the sharing or transfer of electrons, right? So that kind of has now fulfilled that, one of those two different types of bonds here, right? The sharing or transfer, well, the transfer of electrons is referred to in ionic bonding. Now, the other main type of chemical bonding we're going to talk about in this class, and that's going to be saved more so for next chapter in Chapter 10, is covalent bonding. Now, covalent bonding, right, is very different in many different ways compared to ionic bonding. Where ionic bonding is a metal and a non-metal, or a metal and a polyatomic ion, covalent bonding is just straight up non-metals, okay? It's just non-metals. There's no metals involved at all when it comes to covalent bonding. Right, so covalent bonding is between two or more non-metals, right? So there are exactly zero metals involved in covalent bonding at all. Now, where ionic bonding, which we previously looked at, indicates a transfer of electrons. This covalent bonding stuff indicates a sharing of electrons. So that has now kind of fulfilled our two different types of bonding from the definition of chemical bonding, right? Resulting from the sharing or transfer. Well, the sharing portion is dedicated to the covalent bonding, and the transferring portion of the definition is dedicated towards this ionic bonding. Okay. So now we've got these two really distinct differences between ionic bonds and covalent bonds here. The last and third type of bonding that exists, but that we don't really talk too much about in this class, is known as metallic bonding, and it's kind of in the name. It's between two or more metals, okay? And that kind of makes sense, right? It's right in the name there. It's between two or more metals, and that's basically metallic bonding. Now, this table here, it is table E in your reference table. I believe it's on page 3. So if you were to grab your reference table, flip through over to page 3, table E, which is known as your selected polyatomic ions table, has a list of all the different polyatomic ions present on this table, and that we're going to really focus on in this class. Now, the nice thing about this, like anything else on our periodic table or on our reference table, we don't have to memorize any of these polyatomic ions. We just have to be able to recognize them. So what I mean by that is, if we're ever looking at a problem on a test or a problem on a quiz or a homework or whatever, as long as you can recognize any of these polyatomic ions present on table E here in the problem you're doing, that's basically as far as it goes. So as long as you can recognize it in that sample problem, that practice problem, that test or quiz problem, and you can then refer to it in table E here, that's what I need you to know. Okay, again, I don't need you to memorize any of these because they're here. You can always have your reference tables in front of you during tests, quizzes, etc. Okay. So again, no memorizing required here, just recognition, being able to recognize any of these polyatomic ions, right? And we're going to work on that. So it's not important that you recognize all of them now, obviously, but the more we work with them, the more and easier it'll be to recognize them. Now, ion formation. Okay, a little bit of review here. An ion, if we remember, is an atom that has either gained or lost an electron to become a charged particle. And there are two different kinds, right? If you're losing electrons, you're becoming a positive ion, right? These positive ions are called cations, and again, indicates an electron being lost to that, right? And then when it comes to negative ions, right? These negatively charged ions indicate electrons being gained, and these guys are called anions. Okay, so now the formation of an ionic bond. What does that mean, and how do they form? Right. Well, it's pretty simple. Grab my little pen here. Okay, what I'm going to do here, guys, is I'm going to draw the different Bohr models for these two different atoms here. Okay, so a Bohr model for Na is going to come from the electron configuration of Na, or sodium, which is 2-8-1. And then if I look at Cl, Cl has a configuration of 2-8-7. Okay, so these are our two electron configurations for both these. And again, I can always transfer these two electron configurations into their Bohr models. So that's exactly what I'm going to do. Okay, I'm going to take my pen here and create my Bohr model for these two. Okay, so on the first one, I'm going to do my 2 electrons. 2, 3, 3, 4, 5, 6, 7, 8. I'm going to make this one a little more pronounced there. And then 1 right here. Okay. And then try another one right here. 1, 2, 3, and this is a really rough one. Goodness, sorry guys. Okay, so here's 1, 2. Backtrack on that one. Go to the second PEL. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Okay. So now we've got 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 1. So 2, 8, 1 for sodium, and then 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 2, 8, 7 for chlorine. So now what happens here is this. okay? Recognizing, guys, that we're trying to form an ionic bond here. So if I were to go back and take a look at the definition for an ionic bond, that would be referencing the formation of a bond between an atom that is a metal, an atom that is a nonmetal. So just to confirm, if we go to the periodic table and we try and look for and find sodium, or Na here, Na is going to be all the way over here on the left-hand side of the staircase here, right? Our staircase is right here, okay? Left-hand side of the staircase is going to be sodium. So sodium is our metal. I'm going to just use an M to designate metal, right? Capital M to designate metal. Now, chlorine. Chlorine, on the other hand, right, if we look at the staircase, which is over here, to the right of the staircase is chlorine. And hopefully we know at this point that anything to the right of the staircase is a non-metal, okay? So we have a metal bonding with a non-metal to give us an ionic bond, okay? On top of that, since we have now recognized that this is an ionic bond between a metal and a non-metal, this is also going to indicate a transferring of electrons, right? That's an important distinction here. We're not sharing electrons like a covalent bond would be, we're transferring them. Well, where does the transfer come from, right? Who's transferring what? Who's accepting an electron? Who's donating one? Who's giving them away, right? Where is the electrons coming from that are being transferred? Guys, it's all rooted in that idea we've talked about last chapter called our valence electrons. If we look over at the electron configuration for sodium, sodium currently has one valence electron, right? It's the number of electrons in the outermost energy level. If we look over at chlorine, chlorine has 7 valence electrons, okay? So what's going to happen here is if we go to our periodic table to look at sodium, for example, sodium is way over here. If we look at the top right-hand corner for sodium, you guys are going to notice that selected oxidation state, or that charge that we talked about very briefly, right? Top right corner is a +1. Well, if we remember when talking about ions, like we saw in the previous slide there, a positive symbol means we are losing electrons, and the number dictates how many we are losing. Well, that means if Na is going to turn into the Na +1 ion, that means the positive sign means we're losing electrons, and the 1 tells us we're losing 1 electron. Well, if we're losing 1 electron, it just so happens that we're losing this 1 valence electron. So what happens here is this 1 valence electron in the outermost energy level for sodium gets transferred all the way over to our all the way over to our Bohr model for chlorine here to give chlorine its 8. So now our new configuration for the Na plus ends up being 2-8, and our new configuration for the Cl minus ion, right? Because since Cl has now gained 1 electron, right? The gaining of an electron is dictated by the minus sign in an ion, right? The new configuration goes from 2-8-7 to now 2-8-8, because now it has an 8th valence electron in the outermost energy level, okay? And that kind of shows you the formation of an ionic bond here, right? Using Bohr models as an explanation, okay? Now, ionic radius, we talked very briefly about it last chapter, so I'm not going to spend too much time talking about it, but it's important to recognize the differences between atomic radius and ionic radius, right? So if we remember, the atomic radius is the distance from the nucleus of the atom to the outermost electron, right? The ionic radius is the distance for any ion, right? So it's the same thing from the dead center of an ion to the outermost energy level. Now, if you remember, for positive ions, the ionic radius is less than the atomic radius for a neutral atom, and for negative ions, the ionic radius is greater than the atomic radius of a neutral atom. Okay, so again, not a whole lot to write home about. Okay, again, this is a little bit of review from last chapter, so nothing too crazy here. Okay, now noble gas configuration, and this is going to be the last slide I talk about in this video before we see you guys next in class. When an atom gains or loses electrons to form an ion, its electron configuration changes so that it has 8 valence electrons. And we actually saw that just a moment ago when we were looking at the new configurations for the Na plus ion and the Cl minus ion, right? Na plus ended up being 2-8 and Cl minus ended up being 2-8-8. So both of them had an outermost energy level, right, that had a total of 8 valence electrons, right? If we remember, right, 8 being our favorite number in chemistry, right, this fulfills that octet rule. And all these new configurations that form when ions form are called their noble gas configurations. Okay, so that's an example of essentially what we saw in the previous slide. So guys, I'll see you next class.